Radioactivity, a force for good. And a force for bad, however justified the end. In medicine, radioactivity is a boon. For cancer patients, the irradiation of malignant tissue can check, even reverse, the growth of tumors. It works by reducing the vigor of dividing cells. Radioactive material is also used in diagnosis. By injecting a radioactive tracer, the condition of organs like the liver and brain can be visually monitored. Radioactivity comes from unstable atoms. As we fly into an atom, 4 shells of negatively charged electrons orbit a positively charged nucleus. But this cluster of protons and neutrons is inherently unstable. The bigger the nucleus, the greater its instability. This uranium nucleus, with more than 200 protons and neutrons, is specially unstable, and it emits radioactivity. The French physicist Henri Becquerel is the first to notice that minerals containing uranium emit strange penetrating rays. His friends Pierre and Marie Curie, who share with him the Nobel Prize for Physics, study such radioactive minerals and discover radium. And radium, they observe, is unstable. It steadily loses weight as it gives off radioactivity. The New Zealander Ernest Rutherford, working in Britain, shows that heavy elements like radium and uranium emit 3 kinds of radioactivity. He wins the Nobel Prize for Chemistry. The first kind, alpha particles, are the least penetrating and don't even get through a sheet of paper. The second kind, beta particles, are more penetrating. Even so, they're repelled by a thin panel of metal. The third kind of radioactivity is gamma rays, stopped only by a block of lead. Vital in understanding radioactivity are isotopes, different forms of the same atoms. Add 1 neutron to this hydrogen nucleus and it becomes deuterium. Add another and it's tritium. Isotopes of hydrogen. The British physicist Frederick Soddy lays the foundation of isotope theory, and in doing so wins the Nobel Prize for Chemistry. As this nucleus of carbon evolves into 3 different isotopes, however many neutrons latch on, its chemical properties don't change. Its stability does. The Briton Francis Aston discovers many new isotopes, both stable and unstable, and he takes the Nobel Prize for Chemistry. In nature, when unstable isotopes decay, they emit radioactivity. By constantly seeking stability, unstable isotopes split their nuclei. The process is unstoppable. The isotope on the left is decaying twice as fast as the isotope on the right. The faster the decay, the more unstable the isotope, and the more radioactivity emitted. For a triumph in America in 1934, the Italian physicist Enrico Fermi wins the Nobel Prize for Physics. Fermi succeeds in splitting a heavy nucleus of uranium by bombarding it with neutrons. The result? A huge and unexpected emission of radioactivity. The German Otto Hahn, who wins the Nobel Prize for Chemistry, explains what happened in Fermi's lab. The bombarded nucleus, an isotope called uranium-235, had split into daughter nuclei of barium and krypton. This proved that uranium-235 is unstable, for in its common form, uranium-238, the nucleus doesn't split, it's stable. The Danish physicist Niels Bohr spots the potential. Assemble enough uranium-235, the unstable isotope, and you could trigger a chain reaction. A neutron splits a nucleus of uranium-235. As more and more nuclei split, they release more and more neutrons. It's because to hold stable, daughter nuclei need fewer neutrons. Energy and heat soar. The atom bomb is born. A chain reaction in just 1 kilogram of uranium-235. At the University of Chicago in 1942, Enrico Fermi and his team seek a good application for this chain reaction. To control the reaction, they pile 400 tons of graphite blocks around 56 tons of uranium and uranium oxide. When the team withdraws the control rods, the chain reaction, nuclear fission, proceeds safely and smoothly. Nuclear power goes online. In 1956, Britain generates electricity from the world's first commercial fission plant. Today, hundreds of nuclear stations help power the world. They do it by carefully controlling the fission of uranium fuel. The result is vast amounts of energy in the form of heat. This heat generates electricity. The ore that makes uranium fuel comes from deep underground. It's crushed and reduced to a pulp from which uranium can be dissolved. The extract is then combined with magnesium to make a cake containing 75% uranium. Processed into pellets and compiled into long rods, the uranium is finally bundled into fuel rod assemblies, ready for fission. The reactor is a massive steel and concrete building, vital in containing the enormous heat of fission and its harmful radiation. At the reactor core, the fuel rod assemblies are lowered into water. Water acts both as a coolant and as the best medium for an efficient chain reaction. This is controlled nuclear fission, on demand. Heat from the reactor produces the steam that powers the turbines that drive the generators that deliver our electricity. But nuclear generation can go badly wrong. In 1986, at Chernobyl in the Ukraine, a reactor catches fire at this power station. People die and fall sick. And there are long-term effects on all life as a radioactive cloud spreads right across Europe. Archeology benefits greatly from radioactivity. If an artifact contains a radioactive isotope whose rate of decay is known, the specimen can be dated. It's done by comparing the relative amount of the original isotope against its decay products in the specimen. For one dating method, the American Willard Libby receives the Nobel Prize for Chemistry. His invention is radiocarbon dating. It determines the age of organic remains, plants, animals and humans, up to 70,000 years old. A sample of the remains is burned. In the smoke are stable atoms of carbon-12 and unstable atoms of carbon-14, those in white. With a known decay rate, the proportion of carbon-14 to total carbon reveals the date of the sample. In space, for the exploration of our solar system, radioactivity is key. Here, technicians prepare a nuclear generator for blastoff. It's 1997, and the space probe Cassini heads for Saturn. A 7-year journey to a planet so distant that the light of the sun diminishes to just 1% of that on Earth. With solar power impossible, Cassini relies on electricity generated from the heat of a decaying radioisotope.